In our last lesson, we saw how reference counting provides immediate cleanup when an object's count reaches 0. But reference counting has a fatal flaw: circular references. This single problem makes reference counting unsuitable as a standalone garbage collection solution. So what is a circular reference? It happens when two or more objects reference each other, creating a closed loop. Object A points to object B. Object B points back to object A. They form a cycle. Let me show you what this looks like. Here's object A. Here's object B. Now, object A has a reference to object B. We can see the arrow pointing from A to B. But object B also has a reference back to object A. There's an arrow pointing from B back to A. These two objects are now locked in a circular relationship. Each one keeps the other alive. Let's look at a concrete example to see why this is a problem. Imagine we're building a simple application to model a car. A car has an engine. And for our example, the engine also has a reference back to the car. This seems like a reasonable design. The car needs to know about its engine, and the engine might need to know about the car it belongs to. But watch what happens when we combine this with reference counting. We create a new car object. The car object is allocated on the heap. Look at its reference count. It starts at 1 because my underscore car points to it. When the car is created, it also creates an engine object. The engine is allocated on the heap too. Its reference count is also 1 because the car points to it. So far, everything looks normal. Now, here's where the circular reference appears. The car has a reference to the engine. This arrow shows that connection. But the engine also stores a reference back to the car. This curved arrow shows the reference going back. We now have a cycle. Now let's say we're done with the car. We set my underscore car to null. And this removes the external reference from our program to the car object. In a healthy reference counting system, this should start a chain of cleanup. But watch what happens to the reference counts. The car's count is still 1. Why? Because the engine is still pointing to it. The engine's count is still 1. Why? Because the car is still pointing to it. Neither count can reach 0. Even though our program can no longer access either object, their reference counts will never drop to 0. They keep each other alive. Let's understand why this happens. The car's reference count is 1 because the engine points to it. The engine's reference count is 1 because the car points to it. Each object is counting the reference from the other. As long as they point to each other, neither count can reach 0. The reference counting algorithm has no way to detect that these objects are trapped in a cycle. This is a memory leak. The car and engine objects are unreachable by the program. There's no variable in our code that can access them anymore. But they're still occupying memory. The reference counting garbage collector will never reclaim them. If this pattern repeats many times in a program, memory consumption grows until the program runs out of memory and crashes. This reveals the fundamental limitation of reference counting. Reference counting tracks how many references point to an object, but it doesn't track whether the program can actually reach that object. Having references is not the same as being reachable. These objects have references, but the program can't reach them. To solve this problem, we need a different approach. We need to trace the actual paths from the program's roots to the objects in memory. We need to ask not just how many references exist, but whether those references form a path back to the running program. This is exactly what tracing garbage collectors do. In our next lesson, we'll explore the first tracing algorithm, mark and sweep. Subscribe, like, and share.